Okay, so we're going to do the optimization problem. Let me tell my kids to be quiet. Hey, I'm recording. Zip it. Thank you. All right, so optimization problems, all you do is you're typically going to find the absolute maximum or minimum. The reason you're definitely allowed to find the absolute max or min is because you're going to create your own domain with a closed interval, as we're going to do in this example problem here. So you'll be able to find the absolute max or min. Okay. The typical difference between optimization problems and regular problems is that you are going to be writing the equation almost always. You're not going to be given the equation. All right, so these are a couple steps here. Read through them maybe after the fact because it is one of those things that makes more sense after you've done an example. So let's look at the example. This is the one we did in class, but I'm going to go ahead and do it again so that I can explain it more better than I did in class. All right, so we are asked to find the area or to find the length and the width where the area of the rectangle is at a maximum, given that it has to be bounded by this semicircle, which is defined by y equals the square root of 25 minus x squared. Okay, so first of all, think about what you're trying to optimize. Well, you're trying to optimize area. So what you're going to need to take the derivative of is an area equation. All right, an area is equal to base times height, right? Well, in the case of this rectangle here, this is x from 0 to some value is x. This is x as well. So the entire base of the rectangle is 2x. Now, what's the height of the rectangle from here up to here? Well, it's whatever y value you happen to be at, right? Okay, well, a equals 2x times y is going to be difficult to take the derivative of. So what we need to do is take out that y and trade it out for this information right here. We know what y is in terms of x. We want everything in terms of one variable, and that might be something that you have to change. You kind of have to play around with it sometimes and figure out what's going on, but you do need to try to get things in terms of one variable. Maybe it's a radius, maybe it's a height, maybe it's, I don't know, a circumference. Okay, so let's go back to the problem. How do we find the max and the min? Well, we take the derivative. Before we do that, let's make sure we understand the domain that we're working in. The domain that we're working in is between 0 and 5. 1, 2, 3, 4, 5. There's the semicircle. We have to fit somewhere in there. So our domain is 0 to 5. All that does is restrict us to less points, and it gives us some endpoints to test when we get down to that part of the problem. Okay, so let's take the derivative. So we'll do the first one times the derivative of the second one, which this is going to get messy, times the inside, plus the second one times the derivative of the first one. Now, like we talked about in class, we need to clean this up a little bit and then get a common denominator. So I'm going to kind of just work through this and be quiet for a minute. So hopefully you're going to follow along with this. All right. That cancels. Okay, now I'm going to multiply on this term. I'm going to multiply top and bottom by 25 minus x squared, square root of that. So what am I going to get? I'm going to get negative 2x squared plus 2, that's this 2. Now when you say square root of 25 minus x squared times the square root of 25 minus x squared, you just get 25 minus x squared. And in the denominator, when I combine my two fractions here, I just simply have the square root of 25 minus x squared. Excuse me. Now I need to distribute this. I distribute the 2 times the 25 and the times the x squared, and I get negative 2x squared plus 50 minus 2x squared all over the same thing, square root 25 minus x squared. So my final answer here, just for the simplifying part, is 50 minus 4x squared over the square root of 25 minus x squared. Okay, so we're going to use that for our problem. So what I'm going to do is try to copy that. There we go. Oh, there it is. Good. All right, new page. So this is our derivative of the area. Come on. There we go. So we have dA dx is equal to this. All right, now back to the problem. We need to maximize and minimize this. That means we're looking for the maximum or the minimum of the area, which means we need to look for where the derivative is undefined and where the derivative is equal to 0. Okay, well, this fraction right here is undefined when the denominator is equal to 0. So when is the square root of 25 minus x squared equal to 0? Well, it is equal to 0. So if we square both sides, we get 25 minus x squared equals 0, which is the same thing as x squared equals 25, which is x equals plus or minus 5. But the negative 5 was not in our domain, so really all we care about is the x equals to positive 5. You can't have a negative 5 length. Okay, what about when it's equal to 0? Well, if this entire thing here is equal to 0, in a sense, the denominator would cancel out if you did set the whole thing equal to 0, so you just really need to look at the numerator. So 50 minus 4x squared equals 0. So we get 50 equals 4x squared. 50 divided by 4 is 12.5. And so x is equal to plus or minus the square root of 12.5. But once again, the negative is not in our domain. The positive square root of 12.5 is. I don't remember what it comes out to be in a decimal. It's somewhere 3 something. Okay, so what do we need to do next? Well, right now we've got some critical points to test. We've got 5. We've got the square root of 12.5. And then we have our endpoints as well. And our endpoints were 0 and 5. So those are the places we need to test. I'm going to go to the next page. When we test those, we plug them back into the original equation and we see where the max or the min is. So let's plug in 0 first. When you plug 0 into, here's my area equation. When you plug 0 into here, you get 0. If you plug the square root of 12.5 in, you end up with 2 times the square root of 12.5 times the square root of 25 minus, I keep forgetting to put the square root on this, squared. And after you go through just a little bit of work, oh my goodness, you should get 25 out of that. And then lastly, we need to test at 5, and that gives us 0. Okay, so where is our maximum point? That's what we were asked to find. Well, our maximum area is equal to 25. That would be some kind of units squared. They didn't give us units in the beginning of the problem, but it would be the area, the maximum area is 25 units squared when x is equal to the square root of 12.5. All right, well, but if you go back to the beginning of the problem, what we were really asked to find is what is the length and the width when its area is at its max. So we need to take this information, this x equals the square root of 12.5, and figure out the length and the width. Well, the length was 2x, and the width, or the height, doesn't matter what you call it, is the square root of 25 minus x squared. So we're going to take the square root of 12.5 and plug it in here. So our final answer, the length at the maximum area, the length would be equal to 2 times the square root of 12.5, and the width would be equal to the square root of 25 minus the square root of 12.5 squared. This is going to give us the square root of 12.5. Okay, so there is our final answer. There's our length. Here's our width. And we're done. We have found the length and the width for the maximized rectangle inscribed in that semicircle. Okay, I'll talk to you later.